The aircraft is already descending. There is no urgency in the cockpit, no alarms, no abrupt control inputs, only the quiet continuity of routine. An arrival phase conducted thousands of times across the global airspace system every day. Outside, the sky is laid and indistinct. A uniform sheet of high cloud stretches across the horizon, diffusing what little light remains. Below, a thinner layer of mist obscures the ground. There is no clear boundary between sky and terrain, only gradients of gray. The aircraft passes through 8,000 feet. The descent profile is stable. The vertical path is managed by the flight management system, calculated long before the aircraft began its approach. The autopilot remains engaged. Engine thrust adjusts automatically, small and precise corrections maintaining the program glide. Inside the cockpit, the displays glow with soft, controlled brightness. Primary flight displays show no deviation. Airspeed is steady. Altitude decreases predictably. The navigation display presents a clean, geometric path toward the runway. Magenta lines, symmetrical arcs, an ordered abstraction of the world outside. But the outside world is no longer visible. At 5,000 feet, the aircraft enters cloud. The transition is gradual, almost imperceptible at first. The horizon dissolves completely. The last reference to natural orientation disappears, replaced entirely by instrumentation. From this point forward, the aircraft exists within its systems, its position defined not by sight, but by data. This is routine. Modern aircraft are designed for precisely this condition. Redundant systems, satellite navigation, terrain databases, and predictive warnings all function in parallel. The margin for error, statistically, is extremely small. Yet, within this margin, failure does not announce itself. It develops quietly. The descent continues. A minor adjustment occurs, so small it does not immediately attract attention. A change in vertical mode. The autopilot transition from one descent logic to another. The aircraft responds accordingly, altering its pitch by a fraction of a degree. The flight path remains smooth, but the underlying logic has changed. Inside the cockpit, nothing appears abnormal. There are no flashing warnings, no audible alerts, only a subtle shift in how the aircraft interprets its own descent. At 3,000 feet, the approach phase intensifies. Workload increases, not dramatically, but steadily. Checklists are completed. Frequencies are confirmed. Approach minima are reviewed. The runway environment is expected to appear ahead, but outside, there is still only cloud. The aircraft continues descending. The autopilot remains engaged. The descent path, once precisely aligned with the intended glide slope, begins to diverge, slightly at first. The deviation is within tolerance. It does not trigger immediate concern. Modern systems allow for small variations, but the aircraft is no longer exactly where the crew believes it to be. At 2,000 feet, the ground remains invisible. The instrument landing system signals are present, but their interpretation depends on correct mode selection. The aircraft, still stable in appearance, is now following a path that is subtly inconsistent with the published approach. There is no single moment where control is lost. Instead, awareness begins to fragment. Altitude decreases through 1,500 feet. The terrain below is no longer theoretical. It exists, rising gradually, uneven, obscured by weather and darkness. The aircraft systems are aware of it. Terrain databases contain its contours in precise digital form. But awareness within the cockpit depends on interpretation. The aircraft continues descending. At 1,000 feet, the approach should be stabilized. This is a critical threshold in modern aviation. Parameters must be met: speed, descent rate, configuration. If any are outside limits, a go-around is required. From a perspective of raw data, Most parameters appear acceptable, but the vertical path is no longer correct. The deviation, once minor, is now measurable. Still, there is no alarm, only a continuation. The aircraft passes through 800 feet. The cloud layer begins to thin, but the ground does not resolve into clear features. Instead, vague shapes emerge, indistinct patterns of darkness and lighter gray. Without clear visual cues, depth perception is unreliable. The cockpit remains calm. The automation continues to command the aircraft. At 500 feet, the margin for correction narrows significantly. Time compresses. Altitude decreases more rapidly than it appears. Without a stable visual reference, the descent rate is perceived through instruments alone. The human mind, under these conditions, must reconcile expectation with data. An expectation, once established, is difficult to override. The aircraft is now below its intended glide path. The terrain rises to meet it. Inside the cockpit, the instruments continue to display coherent reality, but one that is no longer aligned with the physical world outside. At 300 feet, the first unmistakable cue begins to form. Not visually, but systemically. A condition is developing, one that the aircraft protective systems are designed to recognize. The parameters are approaching a threshold where automated warnings may activate. But thresholds are precise, and time is limited. The aircraft continues its descent. At 200 feet, there is still no clear view of the runway, only fragmented visual references. Incomplete, insufficient. The aircraft remains stable, but stability, in this context, is deceptive. It is the stability of a system following incorrect assumptions. Below 150 feet, the situation becomes irreversible. There is no longer sufficient altitude to analyze, decide, and recover within normal response time. The aircraft is committed to its path, a path that no longer leads to the runway. The final seconds are not chaotic. They are continuous. A descent that began as routine has progressed, step by step, into misalignment, each stage individually acceptable, collectively fatal. The terrain rises silently. There is no dramatic shift in engine sound, no violent maneuver, only the continuation of a descent that should have ended elsewhere. And then, the sequence ends, not with an explosion of action, but with the abrupt absence of continuation. A system that was stable until it was not. A flight that was normal until it was not. A chain of events that did not begin with failure, but with subtle divergence. And in that divergence, unnoticed and uncorrected, the outcome was already forming long before it could be seen. Commercial aviation in the modern era is defined by absence. Absence of uncertainty. Absence of mechanical unreliability. Absence, most of all, of accidents. By the early decades of the 21st century, global aviation had reached a level of safety unprecedented in its history. Millions of flights operated endlessly across continents and oceans, the overwhelming majority concluding without incident. Aircraft systems had evolved into layered architectures of redundancy. Engines rarely failed. Structures were overbuilt and continuously monitored. Navigation, once dependent on ground-based beacons, had become satellite-driven and globally precise. And yet, accidents did not disappear. They changed. Way earlier decades had been defined by mechanical breakdowns and structural limitations. Modern incidents increasingly emerge from complexity, interactions between systems, procedures, and human interpretation. Failures were no longer singular or obvious. They were distributed, subtle, and often invisible until too late. The flight at the center of this investigation was, in every measurable way, routine. It was a scheduled passenger service operating along a well-established route between two major urban centers. The aircraft type was widely used, certified under modern safety standards, and equipped with advanced avionics designed to reduce pilot workload and enhance situational awareness. Nothing about the operation itself suggested elevated risk. The departure had been uneventful. Climb performance was nominal. Cruise altitude was reached on schedule. En route conditions were stable, with only minor deviations required to navigate upper-level weather systems. Air traffic control communications were standard, concise, and unremarkable. From a systems perspective, the aircraft functioned exactly as designed. The destination airport, however, introduced complexity, not through danger, but through precision. It was an airport known for its reliance on instrument approaches during periods of reduced visibility. Seasonal weather patterns frequently produced layered cloud formations, low ceilings, and diffuse lighting conditions. These were not extreme weather events. There were no thunderstorms, no severe turbulence, no convective activity. But there was limitation. Visibility was sufficient for operations, but only within strict procedural boundaries. Approaches into such environments depended heavily on accurate navigation inputs, correct automation modes, and disciplined adherence to stabilized approach criteria. The margin for deviation was narrow, but clearly defined. On the day of the accident, meteorological conditions fell within operational limits. Reports indicated a ceiling low enough to obscure visual reference until late in the approach, with horizontal visibility reduced by mist and atmospheric diffusion. Surface winds were light. There was no precipitation of significance. Temperature and pressure variations were within expected ranges. To an experienced crew, these conditions would not be considered hazardous. They would be considered normal. Air traffic density in the terminal area was moderate. Multiple aircraft were sequenced for arrival, each following standardized routing toward the same runway system. Separation was maintained. Instructions were clear. The rhythm of arrivals, vectoring, descent clearances, speed adjustments unfolded with procedural precision. The accident aircraft was integrated seamlessly into this flow. There were no delays, no unusual instructions, no deviations that would suggest operational difficulty. But modern aviation does not rely solely on external conditions. It relies on internal alignment. Within the cockpit, the transition from cruise to descent represents a shift, not just in altitude, but in cognitive demand. Systems that had been largely passive during cruise begin to require active monitoring. Navigation inputs must be cross-checked. Approach procedures must be briefed and configured. Automation modes must be selected correctly, each with specific implication for aircraft behavior. This transition is structured, but it is also vulnerable, because it depends on interpretation. Modern flight decks present information with clarity, but also with abstraction. Pilots interact not with direct control surfaces, but with layers of logic, autopilot modes, managed versus selected inputs, vertical and lateral navigation constraints. Each mode has meaning. Each selection changes how the aircraft understands its task. And in complex environments, meaning can shift. The approach plan for this flight was not unusual, but it required precision. It involved a descent profile guided initially by the flight management system, followed by capture of a defined glide path aligned with the runway. The transition between these phases, managed descent to final approach, depended on correct configuration and timing. If executed correctly, the aircraft would intercept the glide slope smoothly, descending along a stable path toward the runway threshold. If misconfigured, the aircraft could remain stable, but on an incorrect path. This distinction is critical, because modern systems are designed to maintain stability, not necessarily correctness. They will execute commands exactly as entered. They will follow logic exactly as selected. They will not question intent. By the time the aircraft began its descent toward the destination, all conditions remained within expected parameters. There were no system faults. no abnormal indications, no external disruptions. From the perspective of operational data, the flight was indistinguishable from thousands of others conducted that same day. But beneath this uniformity, a set of dependencies was forming. Dependencies on correct mode awareness, dependencies on continuous monitoring, dependencies on timely recognition of deviation. In isolation, each dependency was manageable. In combination, they created a system that was robust, but not infallible. The history of modern aviation accidents reveals a consistent pattern. Not sudden catastrophe, but gradual divergence. A small misinterpretation, a minor deviation, a momentary lapse in cross-verification. Individually, these elements do not produce accidents. Together, under specific conditions, they can. As the aircraft continued its descent toward the destination airport, it carried with it all the advantages of modern engineering: precision navigation, automated control, predictive warning systems. But it also carried the inherent complexity of those systems, a complexity that does not fail loudly. It fails quietly, and often it fails in a way that appears, for a time, entirely normal. Modern aviation does not fail in isolation. It fails, when it does, across layers. Each functioning is designed, each contributing in ways that are individually logical but collectively misaligned. To understand how a routine descent can evolve into an unrecoverable situation, each layer must be examined separately, not to assign weight to one over another, but to understand how they intersect. Aircraft. The aircraft was representative of its generation, digitally integrated, highly automated, and engineered for precision. At its core was a flight management system designed to construct and execute a complete flight profile. From departure to arrival, the system calculated optimal paths based on navigation data, performance parameters, and environmental inputs. Once programmed, it could guide the aircraft laterally and vertically with minimal manual intervention. The autopilot system interfaced directly with this logic. It did not fly in a human sense. It executed instructions, precise, repeatable, and indifferent to context beyond its programming. Vertical modes controlled how the aircraft climbed or descended. Lateral modes determined how it tracked its route. Each mode had a specific purpose, and transitions between them required correct selection. In normal operations, these transitions were seamless, but they were not automatic in every phase. During descent and approach, the aircraft could operate in multiple vertical modes, each producing a different flight path. Some modes prioritized maintaining a calculated descent profile. Others responded to manual inputs such as selected altitude or vertical speed. The difference between them was not always visually dramatic. An aircraft descending slightly below its intended glide path could still appear stable. The pitch attitude would remain controlled. Engine thrust would adjust smoothly. There would be no abrupt motion, only a gradual divergence from a correct trajectory. This is a defining characteristic of modern systems. They maintain stability, even when the underlying path is incorrect. Crew. The flight crew was trained, certified, and experienced within the operational standards of modern commercial aviation. Their training emphasized procedural discipline, checklists, call-outs, verification steps. Automation management was a core component of this training. Pilots were not only expected to operate the aircraft, but to manage the systems that operated it. This introduced a dual responsibility. They were both operators and supervisors. During high workload phases such as descent and approach, attention must be distributed across multiple domains: monitoring flight path, managing automation modes, communicating with air traffic control, configuring the aircraft for landing, maintaining situational awareness in degraded visibility. None of these tasks, individually, are beyond capacity, but they compete for attention. Modern training addresses this through structured procedures, standard callouts, defined roles, cross-verification between pilots. One pilot flies, the other monitors. Deviations are expected to be identified and corrected early. However, detection depends on expectation. If both pilots share the same assumption about the aircraft's behavior, small inconsistencies may not immediately register as errors. Instead, they are interpreted within the framework of that expectation. This is not negligence. It is a known human factor, confirmation bias within complex systems. In conditions where visual references are absent, reliance on instrumentation increases significantly. Instruments provide accurate data, but they require correct interpretation. A display may show altitude, speed, and vertical trend clearly, but understanding whether those values are appropriate depends on context. And context, in automated environments, is defined by mode awareness. Environment. The environment in which the approach was conducted did not present overt danger. There were no severe weather phenomena, no turbulence strong enough to disrupt control, no wind shear events, no convective systems. Instead, the environment reduced information. Cloud layers obscured the horizon, mist diffused light, eliminating sharp visual cues. Terrain below the approach path was uneven, but not extreme, rising gradually, without prominent features that could be easily distinguished in low visibility. These conditions are common, but they create a specific challenge. They remove external references at the exact moment when precision is most critical. In visual conditions, deviation from the correct path can often be detected intuitively. The runway appears too high or too low in the windshield. The descent angle feels incorrect. Peripheral vision provides depth cues. In instrument conditions, these cues are absent. All perception must be constructed from data. This increases reliance on systems and on the correct interpretation of those systems. Systems, beyond the primary flight controls and navigation logic. The aircraft was equipped with protective systems designed to prevent exactly the type of accident that would later occur. Among these was a Terrain Awareness and Warning System, TAWS. TAWS continuously compares the aircraft's position, altitude, and trajectory against a stored terrain database. If the system detects that the aircraft is in proximity to terrain in a way that suggests risk, it generates warnings, initially advisory, then increasingly urgent. These warnings are designed to be unmistakable. They override routine cockpit audio. They demand immediate response, but they are not predictive in an absolute sense. They operate within defined thresholds, parameters that determine when a situation has become hazardous enough to warrant alerting the crew. Below those thresholds, the system remains silent. This design prevents nuisance warnings during normal operations, but it also means that early-stage deviations may not trigger alerts. In addition to TAWS, the aircraft relied on the Instrument Landing System, ILS, for final approach guidance. The ILS provides lateral and vertical signals, the localizer and glide slope, that define the correct path to the runway. When properly captured and tracked, these signals guide the aircraft along a precise descent angle. However, capturing the glide slope depends on correct configuration. If the aircraft is not in the appropriate mode, or if the capture occurs outside expected parameters, the system may not engage as intended. The aircraft can continue descending, stable in its own logic, but no longer aligned with the ILS guidance. This creates a subtle but critical condition. The aircraft appears controlled, but it is no longer correctly guided. Convergence. Individually, each of these elements, the aircraft systems, the crew's training, the environmental conditions, the protective technologies, represent strength. Together, they form a network, and within that network, accuracy depends on alignment. If the aircraft is in the correct mode, the systems support the crew. If the crew correctly interprets the systems, they maintain situational awareness. If the environment provides sufficient cues, deviations are detected early. If protective systems are triggered, they provide a final barrier. But if alignment is lost, quietly, incrementally, each layer can continue functioning while the overall system begins to diverge. No single failure is required, only a sequence of small, uncorrected mismatches. By the time the aircraft descended below 1,000 feet, that sequence was already in motion. The aircraft was stable. The crew was engaged. By the time the aircraft descends through 1,000 feet above ground level, the outcome is no longer being shaped in large movements. It is being shaped in small ones. Subtle inputs, minor assumptions, a continuation of a path that appears acceptable. This is a phase of flight where modern procedures demand clarity. A stabilized approach must be confirmed. Parameters must align. Speed within limits, descent rate controlled, aircraft configured for landing, and most critically, the vertical path correctly established. From the perspective inside the cockpit, most of these conditions appear satisfied. Airspeed is stable. Configuration is correct. The descent is smooth. But the vertical path, the invisible geometry that defines the aircraft position relative to the runway, is no longer aligned. The aircraft is below it. Midnight, passing 1,000 feet. The aircraft crosses a stabilized approach gate. Under standard operating procedures, this is a decision point. If the approach is not stabilized, a go-around is required. No go-around is initiated. There is no single parameter that demands it. Instead, there is a collective misinterpretation, each value appearing within tolerance when viewed in isolation. The autopilot remains engaged. The descent continues. 020, 900 feet. The instrument landing system signals are present, but the aircraft has not fully captured the glide slope. Instead, it continues in descent mode that maintains a vertical rate based on prior inputs. Consistent, controlled, but no longer synchronized with the precise angle required to reach the runway threshold safely. Inside the cockpit, the deviation is detectable, but detection requires recognition, and recognition depends on expectation. The aircraft appears to be doing what it has been doing for the past several minutes, descending smoothly, predictably. Nothing suggests urgency. 040, 800 feet. Outside, the cloud begins to thin. Shapes form, but they lack clarity. The ground is visible in fragments, dark surfaces, uneven textures, but no definitive reference points. The runway environment does not appear where it is expected. This is a critical cue, but it is also ambiguous. Without clear visual confirmation, the human mind tends to defer to instrumentation, especially when those instruments appear stable. The descent continues. 1 o'clock, 700 feet. The vertical deviation increases. It is no longer marginal. The aircraft is now significantly below the intended glide path. At this altitude, correction is still possible, but it requires immediate recognition and decisive action, either re-establishing the correct path or executing a go-around. Neither occurs. The autopilot continues to follow its selected mode. 115, 600 feet. The terrain awareness and warning system approaches its threshold. Internally, the system evaluates the aircraft's trajectory against the terrain database. The closure rate between the aircraft and the rising ground begins to meet criteria associated with potential risk, but the system has not yet triggered. Its silence reinforces a perception that the situation remains within acceptable bounds. 125, 500 feet. This altitude represents the final margin for a stabilized approach. Below this point, time and altitude are severely limited. The aircraft continues descending. The runway is still not visible. The ground, however, is now more distinct, though still lacking clear definition. The perspective is deceptive. Without proper visual cues, altitude can be misjudged. The descent rate can feel slower than it is. The aircraft is now committed, though this commitment is not yet recognized. 135, 400 feet. The first automated warning activates. A controlled, synthetic voice breaks the continuity of the cockpit. A terrain caution. It is not yet an emergency command, but it is a signal that the aircraft's path is no longer consistent with safe terrain clearance. This is the system's first intervention. The correct response is immediate assessment and, if necessary, discontinuation of the approach. But the warning occurs within an already compressed time frame. Recognition, interpretation, and action must occur almost simultaneously. 140, 300 feet. The warning escalates. The system transitions from caution to command, a directive to climb. At this point, the margin for recovery is minimal. The aircraft is descending below a safe profile, with terrain rising ahead. The autopilot remains engaged, still executing its programmed descent. Disengagement and manual correction are required, but reaction time is limited. 143, 250 feet. The crew initiates a response. Control inputs begin to change. Thrust increases, but the aircraft's inertia, combined with its low altitude, reduces the effectiveness of these inputs. The response, while technically correct, is delayed, not by intention, but by the cumulative effect of earlier misalignment. 146, 200 feet. The aircraft begins to transition from descent to attempted climb. Pitch increases. Engine spool. But the terrain closure rate remained critical. The aircraft does not have sufficient vertical separation to fully recover within the available distance. 148, below 150 feet. The final seconds are continuous. There is no abrupt loss of control, no structural failure, only a trajectory that can no longer be corrected in time. The ground, previously abstract, becomes immediate. The aircraft, still largely intact and under partial control, descends into terrain. Impact. The sequence ends without spectacle. No dramatic maneuver. No sudden deviation from physics. Only the conclusion of a descent that began correctly, continued normally, and diverged subtly until correction was no longer possible. Silence. After impact, the systems that had guided the aircraft, precise, reliable, and consistent, cease to function. The data stream ends. The flight, defined by continuity, ends in interruption. This was not a loss of control in the traditional sense. It was a loss of alignment. A stable aircraft, a functioning system, a trained crew, all operating within a framework that, step by step, allowed a deviation to persist until it became irreversible. In the immediate aftermath, there is no clarity, only location. The accident site is identified through a combination of last known radar position, emergency locator transmissions, and reports from nearby observers. The terrain, already a limiting factor during the approach, now defines access. Recovery teams move toward the site with precision, not urgency, because urgency no longer changes outcome. The aircraft has come to rest short of the runway environment. There is no ambiguity about the sequence, but there is no explanation. Yet, initial response. Emergency services arrive in stages. Fire suppression, medical teams, and security units establish a perimeter. The priority is containment, ensuring that any residual hazards are controlled, that access is restricted, and that the site remains intact for investigation. Modern accident response is structured. Every action is documented. Every movement is controlled, because within the debris field lies data. And in modern aviation, data defines truth. The recorders, the flight data recorder, FDR, and cockpit voice recorder, CVR, are located within the wreckage. Their positions are known by design, installed in the aft section of the aircraft, engineered to survive impact forces and post-accident conditions. Recovery teams prioritize their retrieval, not because they are symbolic, but because they contain the only continuous record of the aircraft's final moments. Once recovered, they are transported under controlled conditions to an analysis facility. There is no interpretation at the site, only preservation, reconstruction. The investigation begins not with conclusions, but with reconstruction. Data from the FDR is extracted, hundreds of parameters recorded multiple times per second. Altitude, airspeed, vertical speed, autopilot modes, control inputs, engine performance, navigation signals. Individually, these parameters are factual. Together, they form a timeline. The CVR provides context, not emotion, not narrative, but environment, background sounds, system alerts, the cadence of routine operations, the absence or presence of urgency. When synchronized with flight data, it allows investigators to align action with condition. Second by second, early findings. The initial analysis reveals a pattern consistent with modern accident profiles. There is no evidence of mechanical failure. Engines were producing thrust. Flight control systems responded to inputs. Navigation systems were operational. The aircraft was, by all technical definitions, airworthy. The descent profile, however, shows divergence. At a specific point during the approach phase, the aircraft transitions into a vertical mode that does not correspond to the intended glide path. From that moment onward, the aircraft maintains a stable descent, but a rate and angle inconsistent with the instrument landing system guidance. This is not an abrupt change. It is gradual, but it is continuous. Mode awareness. Attention shifts to automation. The autopilot did not fail. It executed commands exactly as configured. The critical question becomes, why was the aircraft in that mode? Analysis of control panel inputs indicates that a selection was made during the descent phase, one that altered how the aircraft managed vertical navigation. This selection was valid within the system's logic. It did not generate an error. It did not produce a warning, but it required recognition, because it changed the relationship between the aircraft and the glide path. From that moment, the aircraft was no longer descending according to the approach design. It was descending according to a different logic, one that remained internally consistent, but externally incorrect. Crew interaction. The CVR provides insight into workflow. There is no evidence of confusion in a conventional sense. No raised voices. No indications of panic. The environment remains controlled, but there is a pattern. Call-outs related to altitude and descent continue. Cross-checks occur, but they are incomplete. The vertical deviation, though present in the data, is not identified in time. This is not due to absence of information. It is due to interpretation. Both pilots appear to share the same understanding of the aircraft state. That understanding is consistent with the mode they believe the aircraft to be in, not the mode it is actually operating under. This alignment of perception, while normally beneficial, becomes a vulnerability because it reinforces itself. The warning system. The terrain awareness and warning system activates within expected parameters. Its timing is precise. The first caution occurs when the aircraft projected path intersect with terrain within a defined threshold. The subsequent warning escalates appropriately as the risk increases. The system performs exactly as designed, but design includes assumptions. It assumes that warnings will be recognized immediately and acted upon without delay. In this case, the warning occurs at an altitude where response time is limited. The delay between warning and corrective action, measured in seconds, is sufficient to reduce the effectiveness of recovery. Contributing factors. The investigation does not identify a single cause. Instead, It defines a chain. Incorrect autopilot mode selection during descent. Failure to detect deviation from glide path. Reduced visual cues due to environmental conditions. Delayed response to terrain warning. Continuation of approach below stabilized criteria. Each factor is individually survivable. Together, they form a sequence that leads to impact. This is a defining characteristic of modern aviation accidents. They are systemic. Industry response. Preliminary findings are shared with regulatory authorities, the aircraft manufacturer, and the operator. There is no immediate grounding of fleets. No emergency directive based on mechanical failure. Instead, the focus shifts to procedures. Training programs are reviewed. Automation management practices are examined. The emphasis is not on what failed, but on how it was understood. Because the systems, in this case, did not malfunction. They were followed. Impact. Beyond the technical findings, there is consequence. Operations are paused. Airlines review approach procedures into similar environments. Briefings are updated. Simulators are reprogrammed to replicate the scenario, not as an anomaly, but as a training case. The accident does not introduce a new hazard. It reveals an existing one. Conclusion of investigation phase. The final report will not describe a catastrophic failure. It will describe continuity, a sequence in which each step followed logically from the one before it, until the collective outcome could no longer be altered. The data will be precise, the conclusions measured, and the implications quiet but far-reaching. In modern aviation, accidents do not end with impact. They continue in reports, in training rooms, in redesigned procedures, and in the quiet adjustments made to systems that, until a specific moment, appeared sufficient. The event is no longer an isolated occurrence. It becomes a reference. Understanding the outcome, the investigation does not conclude with a single failure. There is no broken component to replace, no structural weakness to reinforce, no system to remove from service. Instead, the findings describe a condition, a stable aircraft, guided by correct systems, following an incorrect understanding. This distinction matters because it shifts the focus from hardware to interaction, from failure to interpretation. Automation reconsidered. Automation remains central to modern aviation. It reduces workload, increases precision, and allows crews to manage complex environments with consistency. But its reliability introduces a paradox. The more dependable a system becomes, the less frequently it is questioned. Following this accident, emphasis is placed not on reducing automation, but on reframing its role. Pilots are reminded, automation does not replace awareness. It requires it. Training programs begin to incorporate deeper analysis of mode behavior, not just how to select modes, but how to verify them continuously. Crews are encouraged to cross-check not only what the aircraft is doing, but why it is doing it. Mode awareness becomes an active process, not an assumption. Procedural reinforcement. The concept of a stabilized approach is revisited. It already exists as a fundamental safety barrier, clearly defined, mildly taught, consistently applied. But this event highlights a limitation. Parameters can appear stable, while the overall trajectory is not. As a result, procedures evolve. Greater emphasis is placed on vertical path verification, ensuring that the aircraft is not only descending smoothly, but doing so along the correct geometric profile. Instrument cross-checking becomes more deliberate, less routine. Callouts are refined. Training scenarios introduce subtle deviations, cases where the aircraft appears stable but is misaligned. Crews are trained to detect these conditions earlier, before altitude limits reduce available options. Terrain awareness and response. The terrain awareness and warning system performs as designed. Its role is not to prevent all deviations, but to provide a final barrier when those deviations become hazardous. However, the timing of its activation, close to the ground, reinforces a critical principle. Warnings are last lines of defense, not primary safeguards. In response, training emphasizes immediate, decisive action upon receiving terrain warnings. The concept is simple, but reinforced with clarity. A warning is not a suggestion. It is a command. There is no requirement to confirm, no need to analyze, only to act. Human factors. Perhaps the most enduring lesson lies not in systems, but in perception. The crew did not ignore information. They interpreted it within a shared understanding. This alignment, normally beneficial, became a constraint because it limited the range of interpretation. Modern training begins to address this more directly. Crews are encouraged to challenge consistency, to question situations where everything appears normal, but context is incomplete. The absence of alarms is no longer considered reassurance. Only confirmation is. Industry-wide influence. The impact of the accident extends beyond a single operator. Regulatory bodies review guidance on automation management. Manufacturers examine interface design, how modes are displayed, how transitions are indicated, how clearly the system communicates its current logic. Changes are not always visible to passengers. They are embedded in software updates, in training modules, in procedural documents. Small adjustments, but cumulative, a quiet legacy. Over time, the accident becomes part of a larger pattern, one that defines a modern era of aviation safety. Not a pattern of frequent failure, but a pattern of rare, complex events that reveal how precision systems and human interpretation can diverge. The lessons are integrated gradually. They do not eliminate risk. They refine it. They narrow the conditions under which similar sequences can occur. Final reflection. The flight began as routine. Every system functioned. Every procedure was available. Every safeguard existed. And yet, alignment was lost. Not suddenly, not dramatically, but step by step. In modern aviation, this is where risk resides. Not in what is visible, but in what is assumed. Closing. There is no single moment to isolate. No definitive point where the outcome became inevitable. Only a sequence, continuous, logical, and quiet. A descent that did not appear unsafe. A system that did not appear incorrect. A situation that did not announce itself until there was no time left to change it. The legacy of such events is not fear. It is awareness. An understanding that safety is not maintained by systems alone, but by the constant alignment between system behavior and human perception. And that alignment, once lost, must be recognized early, while there is still time to act.